The dream of Mars sounds inspiring until you ask one terrifying question. What happens when the astronauts try to come home? Because hidden beneath every cinematic vision of humans standing on the red planet is a brutal engineering reality that almost nobody talks about honestly. A Mars mission is not just about landing safely. It is about trusting a machine left abandoned for nearly 2 years in one of the harshest environments in the solar system and believing that at the exact moment human lives depend on it, that machine will ignite perfectly. The deeper you examine the physics, the more disturbing the truth becomes. Under current engineering limits, returning from Mars may be far more dangerous than reaching it in the first place. Human civilization has built a powerful narrative around Mars. The red planet is presented as humanity's next frontier, our backup world, the first great step toward becoming an interplanetary species. Space agencies and private companies speak about launch windows, colony plans, fuel production systems, and permanent habitats with incredible confidence. But inside all of those ambitious blueprints sits one fragile assumption that rarely receives enough public scrutiny. The assumption is that a rocket sent from Earth, landed on Mars, and left completely alone for over a year will still function flawlessly when it is finally asked to launch again. That assumption collapses the moment physics enters the conversation. To understand why, you have to stop thinking about Mars as an adventure and start thinking about it as a hostile thermodynamic system. The greatest enemy on Mars is not gravity, it is time itself. More specifically, it is entropy, the slow and unavoidable process through which all organized systems degrade. A Mars ascent vehicle would not simply sit quietly waiting for astronauts to return. Every second it remained on the surface, microscopic damage would accumulate across its engines, seals, fuel systems, electronics, and structural components. Imagine taking the engine of a high-performance aircraft, removing all protective coverings, and leaving it exposed inside an endless chemically reactive sandstorm for 2 straight years. Temperatures swing violently every day. Dust invades every microscopic opening. Lubricants begin breaking down. Metal contracts and expands again and again under thermal stress. No technicians arrive for maintenance. No replacement parts exist. Then after 24 months, someone demands that engine suddenly operate at maximum power perfectly on the first attempt. Nobody familiar with engineering would trust that system with their life. Yet that is almost exactly what a Mars return mission demands. The reason becomes even more brutal when we examine the rocket equation, one of the most unforgiving relationships in all of physics. The equation governs how rockets move, and it punishes mass with extraordinary cruelty. A Mars ascent vehicle must carry enough fuel to launch astronauts off the surface, reach Martian orbit, and reconnect with a return craft capable of traveling back to Earth. But every kilogram added to protect the rocket from Mars also increases the amount of fuel required. More shielding means more mass. More mass means exponentially more propellant. More propellant means a larger rocket, which itself requires even more propellant to transport from Earth in the first place. This creates a vicious cycle that engineers cannot escape through optimism alone. At first glance, the solution sounds simple. Add stronger insulation, add protective coverings, add backup systems, add reinforced seals, but the rocket equation does not negotiate. Each additional kilogram added for safety rapidly multiplies the fuel demands of the mission. Eventually, the numbers stop behaving like engineering targets and start behaving like physical impossibilities. That is why most mission concepts quietly rely on a dangerous compromise. They assume the Martian environment will not damage the return vehicle faster than expected, but Mars is not forgiving. The thermodynamics alone are devastating. Modern rocket engines require cryogenic propellants, especially liquid oxygen and liquid methane. These fuels only remain stable at unbelievably low temperatures. Liquid oxygen must stay near minus 183 degrees Celsius. Liquid methane must remain around minus 161 degrees Celsius. If the temperature rises above those thresholds, the liquids begin boiling into gas and escaping from storage tanks. This process is known as boil-off, and it represents one of the greatest hidden threats to any Mars return mission. Even tiny amounts of daily fuel loss become catastrophic across hundreds of days. A crew on Mars would likely wait more than a year before planetary alignment allows a fuel-efficient return to Earth. During all that time, the propellant tanks would constantly absorb heat from the surrounding environment. No insulation system is perfect. Heat always moves from warmer regions to colder ones. That is not an engineering opinion. It is the second law of thermodynamics. So day after day, the fuel slowly disappears. Engineers propose active refrigeration systems to stop the boil-off, but those systems create new problems. Refrigeration requires continuous electrical power. It introduces moving parts that can fail. It adds more weight. It demands maintenance. Every new layer of complexity becomes another point where entropy can attack the mission. And then comes the most dangerous part of all, the dust. Martian soil is not harmless dirt. It contains highly reactive chemicals called perchlorates that aggressively corrode both organic materials and metals. The dust particles themselves are jagged and razor-sharp at microscopic scales because Mars lacks the flowing water that smooths grains on Earth. Worse still, the thin Martian atmosphere allows the dust to accumulate strong electrostatic charges, causing it to cling stubbornly to every surface it touches. The dust gets everywhere. It penetrates seals, fuel valves, mechanical joints, injector systems, electrical contacts, and moving components. Over time, tiny particles begin interfering with systems that require extreme precision to function correctly. A fuel injector slightly blocked by dust may disrupt combustion ratios. A brittle seal, weakened by thermal cycling, may crack under pressure. A latch, contaminated by abrasive particles, may fail to release during ignition. The terrifying part is that these failures often remain invisible until the exact moment the rocket attempts to launch. There is no warning, no second attempt, no repair crew standing nearby. If a Mars ascent vehicle suffers even a partial engine failure during launch, the result is not usually a safe shutdown. It is violent destruction. And this is the reality many futuristic presentations avoid discussing honestly. Returning from Mars is not a single engineering problem. It is dozens of brutal physical challenges all stacked together simultaneously. Cryogenic fuel preservation, long-term material durability, corrosion resistance, thermal fatigue, dust infiltration, seal integrity, mechanical reliability. Every one of them must work perfectly together after sitting abandoned on another planet for over a year. A system that is 98% functional is still a system capable of killing everyone inside it. That is why the true obstacle between humanity and Mars is not distance. It is reliability against entropy. It is the microscopic crack in a frozen seal, the invisible dust particle inside a fuel valve, the slow leak nobody notices until ignition begins. Physics does not care about ambition. Thermodynamics does not reward courage. The universe follows its laws with complete indifference. And until humanity learns how to defeat those laws on Mars with absolute reliability, the dream of standing on the red planet and safely returning home remains one of the greatest unsolved engineering challenges in human history. If you enjoyed this deep exploration into the hidden physics behind Mars missions, make sure to like the video, subscribe to the channel, and turn on notifications because the next part goes even deeper into the terrifying realities space agencies rarely discuss publicly. The deeper scientists study Mars return missions, the clearer one disturbing reality becomes. The greatest danger is not the launch from Earth, the landing on Mars, or even the radiation exposure during the journey. The real danger begins after everything appears successful, after the crew has landed, after the headlines celebrate humanity's arrival on another world, after the cameras stop broadcasting. Because from that moment forward, every second becomes a countdown toward mechanical decay. The return rocket sitting silently on the Martian surface is no longer just a machine. It becomes a battlefield between human engineering and the unstoppable laws of entropy. And according to the physics, entropy usually wins. To understand the severity of the situation, you have to appreciate how incredibly fragile rocket systems really are. Modern spaceflight looks powerful from a distance, but rockets only function because thousands of delicate systems operate within microscopic tolerances. A tiny imbalance in fuel flow can destroy an engine. A seal smaller than a human finger can determine whether a launch succeeds or explodes. On Earth, these systems survive because they are constantly monitored, repaired, inspected, and replaced by massive engineering teams. Every launch on Earth happens after endless testing and maintenance. Mars offers none of that support. Once astronauts arrive, the return vehicle is completely isolated. No replacement engines can be delivered quickly. No emergency technicians can land nearby. No industrial repair facilities exist. Every problem must either be solved by the astronauts themselves or remain unsolved permanently. And unfortunately, Mars is one of the worst possible environments for long-term machinery survival. One major reason is thermal cycling. Mars experiences dramatic temperature swings between day and night. Temperatures can rise relatively high during the daytime and then plunge to brutally cold levels after sunset. These repeated changes force materials to expand and contract continuously. Metal components stretch microscopically under heat and shrink again under freezing conditions. Over hundreds of cycles, these tiny movements create stress fractures invisible to the naked eye. This process is already a serious problem on Earth. Aircraft experience metal fatigue. Bridges develop microscopic cracks. Industrial systems wear down from repeated thermal stress. But Mars magnifies the problem because the environment is so extreme and because no maintenance infrastructure exists to catch failures early. Imagine a fuel line exposed to hundreds of violent temperature transitions over 18 months. Tiny cracks begin forming deep inside the material structure. Eventually, those cracks spread. Maybe the line still looks perfect from the outside. Maybe every sensor still reports normal conditions. But during launch, when supercooled fuel suddenly rushes through the system under enormous pressure, that hidden fracture becomes catastrophic. And rockets do not tolerate catastrophic failures gently. The combustion chambers inside rocket engines operate at pressures and temperatures so extreme that even a minor defect can trigger total destruction within milliseconds. Engineers on Earth spend years preventing exactly these kinds of failures. They constantly inspect engines using advanced imaging systems, replace worn components, and carefully monitor material fatigue. On Mars, astronauts would have limited tools, limited spare parts, and limited diagnostic capabilities. The situation becomes even worse when we examine lubrication systems. Most moving mechanical systems rely on lubricants to reduce friction and wear. But lubricants behave unpredictably under Martian conditions. Extreme cold thickens fluids and changes their chemical properties. Dust contamination turns lubricants into abrasive compounds. Over time, moving components that once operated smoothly begin grinding against each other. Bearings wear down, hinges stiffen, mechanical actuators lose precision. A tiny amount of additional friction inside a critical valve may not sound dangerous, but rocket systems depend on perfect timing and exact mechanical responses. A valve opening milliseconds too slowly can destabilize combustion. A release mechanism partially jammed by dust may fail under launch stress. Again, these failures often remain invisible until the exact moment they become deadly. Then there is the issue of power generation. A Mars ascent vehicle cannot simply sit dormant for 2 years. It must continuously power refrigeration systems, communication systems, diagnostic equipment, and environmental controls. Most proposed missions rely heavily on solar panels or nuclear systems for energy, but Mars creates serious challenges for both. Solar panels slowly lose efficiency as dust accumulates across their surfaces. The problem is far worse on Mars because the dust is electrostatically charged and aggressively sticks to everything. NASA's robotic rovers have already demonstrated how dangerous this can become. Dust storms can darken the sky for weeks, drastically reducing available sunlight. Panels slowly suffocate beneath layers of fine, abrasive material. Human missions would require vastly more power than robotic rovers ever needed. Refrigeration systems preserving cryogenic fuel cannot simply shut down during a storm. Communication systems cannot stop operating. Life support systems cannot pause because sunlight disappears. If solar efficiency drops too far, the entire return mission may become impossible long before launch day arrives. Nuclear power sounds like a solution, but it introduces different risks. Nuclear reactors add enormous complexity, additional mass, radiation shielding requirements, and long-term reliability concerns. Once again, every added system creates new opportunities for failure. This is the hidden reality most public discussions avoid. Mars missions are not defeated by one dramatic obstacle. They are threatened by thousands of tiny failures accumulating slowly over time. Entropy works patiently. One cracked seal, one contaminated valve, one weakened fuel line, one frozen actuator, one dust-covered solar panel. Individually, these issues seem manageable. Together, they create an environment where survival depends on near-perfect engineering operating continuously without support in one of the harshest locations humanity has ever attempted to enter. And then there is the psychological dimension, which becomes deeply connected to the engineering itself. Astronauts on Mars would know every single day that their survival depends entirely on the health of a machine sitting outside in the dust. Imagine waking up each morning aware that the only vehicle capable of bringing you home is slowly degrading in silence. Every dust storm becomes terrifying. Every unexplained sensor fluctuation becomes emotionally devastating. Every strange sound inside the habitat raises questions nobody can answer confidently. Because unlike missions in low Earth orbit, Mars offers no rescue option. If something critical fails, nobody is coming. The nearest human beings would be hundreds of millions of kilometers away. Communication delays ranging from several minutes to nearly half an hour would make real-time troubleshooting impossible. Astronauts would often face emergencies completely alone, relying only on whatever tools and training they carried with them. This isolation changes the meaning of engineering risk entirely. On Earth, engineers often solve problems through iteration. Something fails, lessons are learned, systems improve. Mars does not allow that luxury. The first crew may only get one attempt to survive. There is no room for gradual learning curves when every failure happens millions of kilometers from home. And despite all these dangers, the harshest truth may still be this. Current technology has never demonstrated the long-term reliability required for a true Mars return mission. Humanity has never operated a fully fueled ascent vehicle for over a year in Martian conditions and then successfully launched it back into orbit with human passengers aboard. Not once. That does not mean Mars missions are impossible forever, but it does mean the confidence often surrounding these discussions is far ahead of the proven engineering reality. The gap between inspiration and operational survival remains enormous. The universe is not hostile in an emotional sense. It simply follows physical laws without compromise. Mars does not care about human ambition. Thermodynamics does not negotiate with optimism. Material fatigue does not pause for courage. Every successful Mars return mission will require humanity to defeat not one obstacle, but an entire ecosystem of interconnected physical failures operating together over immense stretches of time. And right now, the physics suggests we are still learning how difficult that challenge truly is. If you want to continue this journey into the hidden realities of interplanetary survival, subscribe to the channel, like the video, and stay tuned because the next part explores the terrifying medical and biological dangers astronauts may face long before they ever attempt to leave Mars behind. The greatest danger of a Mars mission may not be mechanical failure at all. It may be the human body itself. Because while engineers struggle against fuel loss, dust infiltration, and thermal degradation, another battle unfolds quietly inside the astronauts. A battle against radiation, gravity loss, cellular damage, and biological deterioration. And unlike damaged machinery, the human body cannot simply be repaired with replacement parts. Once certain systems begin failing, there may be no way back. For decades, space exploration has focused heavily on propulsion systems and vehicle design. But the deeper scientists study long-duration space travel, the clearer one disturbing truth becomes. Human beings evolved under an incredibly specific set of planetary conditions. Earth's gravity, atmosphere, magnetic field, pressure, oxygen balance, and radiation shielding shaped every aspect of human biology over millions of years. The moment astronauts leave Earth for a Mars mission, they leave behind the environmental protections their bodies were built to depend on. And the damage begins almost immediately. The journey to Mars alone may take between 6 and 9 months, depending on planetary alignment and propulsion capability. During that entire time, astronauts would exist in microgravity. At first glance, floating weightlessly through space appears harmless, even beautiful, but biologically, the human body interprets weightlessness as a catastrophic environmental change. Muscles begin shrinking because they are no longer needed to support body weight. Bone density decreases as the skeletal system stops carrying normal mechanical loads. Studies from the International Space Station show astronauts can lose significant amounts of bone mass during extended missions despite rigorous exercise programs. The body essentially starts dismantling itself to conserve energy. The problem becomes terrifying when combined with Mars' gravity. Mars only provides about 38% of Earth's gravity. That means astronauts arriving after months in microgravity would step into an environment still far too weak to fully restore normal biological function. Their muscles would already be weakened, their cardiovascular systems altered, their balance systems disrupted, their bones partially degraded. And yet these same astronauts may eventually need to perform one of the most physically demanding tasks imaginable, surviving a Mars ascent launch under extreme acceleration forces while operating critical systems perfectly under pressure. The human body may simply not be prepared for that level of stress after years away from Earth. But gravity loss is only the beginning. Radiation exposure during a Mars mission represents one of the most severe biological threats ever faced in human exploration. Earth's magnetic field acts as a giant invisible shield, deflecting enormous amounts of harmful cosmic radiation and solar particles away from the planet's surface. Mars lacks that protection. Space between planets offers even less. Astronauts traveling to Mars would spend months exposed to deep space radiation levels far beyond anything experienced during missions in low Earth orbit. Highly energetic particles moving near the speed of light would constantly pass through their bodies, damaging DNA, increasing cancer risk, and potentially affecting brain tissue itself. This is not theoretical speculation. Studies already suggest prolonged exposure to cosmic radiation may alter cognitive performance, memory function, and neural structure. In animal experiments, radiation exposure similar to deep space conditions has been linked to inflammation inside brain tissue and impaired decision-making abilities. Now imagine the implications. A Mars crew may spend years isolated in one of the most dangerous environments humans have ever entered while slowly accumulating neurological damage from radiation exposure. The very people responsible for operating the return vehicle may not possess the same cognitive sharpness they had when the mission began. And there is another horrifying detail many people overlook. Radiation damage accumulates invisibly. Astronauts would not necessarily feel it happening. There may be no immediate symptoms. Cellular mutations, vascular injury, and neural degradation could progress silently for months before becoming detectable. Then there are solar storms. The sun periodically releases enormous eruptions of energetic particles known as coronal mass ejections. On Earth, our magnetic field protects us from most of their effects. In deep space, astronauts would be dangerously exposed. A sufficiently powerful solar event during transit could deliver lethal radiation doses within hours if proper shielding is unavailable. This creates a terrifying engineering dilemma. Effective radiation shielding requires mass, but as we already discussed, the rocket equation punishes additional mass severely. Heavy shielding makes missions exponentially more difficult and expensive. Once again, physics creates a trap with no simple solution. Even if astronauts survive the radiation exposure, Mars itself presents additional biological dangers. The Martian environment is incredibly dry, chemically reactive, and filled with toxic perchlorate compounds. Fine dust particles could enter habitats and potentially contaminate air systems. If inhaled repeatedly, these particles may damage lung tissue over time. Scientists still do not fully understand how prolonged exposure to Martian dust might affect human health because no human has ever experienced it directly. And then comes isolation. A Mars mission would likely become the most psychologically extreme expedition in human history. Astronauts could spend nearly 3 years away from Earth when travel time and surface operations are combined. Communication delays prevent real-time conversations with mission control or family members. Depending on planetary positions, delays may reach over 20 minutes each way. Think about what that means emotionally. No immediate help, no instant advice, no natural human conversation. Every message arrives from the past. The crew would exist inside profound psychological isolation while living under constant awareness that a single failure could trap them permanently on another planet. Research from isolated environments on Earth already shows how confinement and isolation can affect mental health. Antarctic stations, submarine crews, and long-duration simulations reveal increased risks of depression, anxiety, sleep disruption, interpersonal conflict, and cognitive fatigue. Mars would amplify every one of those pressures dramatically.